Now we'll talk about combinations. I often liken combinations to my order of a pizza. I don't care what order they put the toppings on my pizza for the most part. I think it's generally accepted that the pepperoni goes on, or the sauce goes on first, but that might be weird if it didn't. But if I order a pizza with pepperoni and jalapenos, I don't care what order they put the pepperoni or the jalapenos on there. I just care that there's a lot of pepperoni and a lot of jalapenos on there, and I'll be satisfied with my pizza. So my choices of pepperoni and jalapenos, not mattering which one went first or which one went second, would be an example of a combination, whereas a permutation, that would be different. Putting the pepperoni on first, followed by the jalapenos, would be different than the jalapenos followed by the pepperoni. So that's kind of the key difference between combinations and permutations. Here we have a formula for finding the number of combinations. We have this n choose r, C for combination right there. We have n factorial in the numerator, and in the denominator we have r factorial over this quantity times this quantity n minus r factorial as well in the denominator with that. So if we wanted to see an example, let's do the same one a second ago. We did for a permutation, we did I think we did 10, choose 4 for the permutation. So we'll do 10, let's do 10C4 here. Let's figure out the number of different combinations of 4 things I can make out of 10 with that. So let's go ahead and plug this in. We would have 10 factorial in our numerator. In our denominator here, we have r factorial, so we have a 4 factorial. And then here we would have a 10 minus 4 factorial, which is actually 6 factorial. So I have 10 factorial over 4 factorial times 6 factorial in my denominator. Now, to simplify this, I'm going to start breaking the 10 factorial down again until I hit the largest of the factorials in the denominator, which, just like in the other example, in this case would be 6 factorial. So I do 10 times 9 times 8 times 7 times, instead of saying 6 times 5 times 4 times 3 times 2 times 1, I'm just going to say times 6 factorial. Now, what that actually allows to happen is that the 6 factorial right there can cancel out from the numerator and denominator. So now I'm left with 10 times 9 times 8 times 7 in my numerator. In the denominator, 4 factorial means 4 times 3 times 2 times 1. Don't forget to expand that. And I'm going to go ahead and do a little bit of simplification here now. Sure, I've got the numbers small enough that my calculator could probably handle them, but I can cancel a little bit out here as well. I see an 8 in my numerator, and I actually see 2 factors in my denominator that would produce 8. 4 times 2 makes 8. So that 4 and that 2 together can cross off that 8 completely. And then I look down here, this 3 that's in my denominator actually goes into one of my factors of my numerator. 3 goes into 9 3 times. So I can cross off the 3 there, cross off the 9, and replace it with a 3 there. I basically just did 9 divided by 3, and that was 3. So I'm just left needing to compute, and I'm running out of room, so I jump up here. I have 10 times 3 times 7 that I have to go ahead and compute. That's all that was remaining. I don't need to worry about the 1 in the denominator. I don't have anything else in the numerator other than those 3 factors. 10 times 3 is 30. 30 times 7 would be 210. So there are 210 combinations of 4 things out of a group of 10. Whereas when we talk permutations, there were 5,040 unique permutations where the order made a difference. Combinations, when the order is not important, there's significantly less ways to do